All right, so purpose of this lab, guys, is simply to investigate the work energy theorem stuff that we've been talking about, okay, and have a look at how efficient are some of these conversions that we've been looking at in class, specifically something moving up or down a ramp. In this case, it's going to be down a ramp, okay? We're simply going to put the cart at the top of the ramp and let it go down, okay? And we're going to compare the potential energy at the top of the ramp with the kinetic energy at the bottom of the ramp. Okay? Now when you're thinking about your design and variables here, I want you to think about this. The only way this experiment happens is if there's what at the beginning of the experiment? Right. Okay? We can't compare the kinetic energy at the bottom to anything if we don't have potential energy at the top. Those are the two things we're comparing. Okay? So we're giving it potential energy. It's kind of big, giving it the potential energy. Okay? We're doing work. We're lifting the cart to the top of the ramp. Okay? And then we're allowing it to roll down the ramp and convert that into kinetic energy, and those two things are being compared. That's all we're comparing, is those two values. Now, we're going to do 3 trials, okay? But the 3 trials are going to be exactly the same. We're not going to change the ramp any. It's just so that we can get a nice average of the 3, okay? Because sometimes you get one run where the car wobbles a little bit more than the others, and we just want to have some consistency. So we are doing 3 trials, but we're not really comparing the 3 trials. We're just averaging the data from the 3 trials for the sake of consistency, okay? So the way this will work is, okay, when you have the cart going down the ramp, are you going to do anything to the ramp while the cart is on it? Okay. What's pulling it down the ramp? Yeah, or the parallel component of it, yeah. Okay, but it's the result of gravity, so gravity might be something you want to consider as something you list in your design, right? Because it's, you know, consistent and not changing throughout the experiment. Hint, hint. Okay. Now, for our hypothesis, okay, we need if and then statement that's looking at kinetic and potential energy and kind of incorporating work energy theorem, right? So the if part of our hypothesis should probably just say what should, okay, or what the theoretical relationship would be between, okay, the energy at the top of the ramp and the energy at the bottom of the ramp, the theoretical relationship. So I'm thinking kind of like conservation of energy here. Okay, so the idea here, or the idea of the conservation of energy is that the energy that is given at the top of the ramp is conserved, right? It should be there at the bottom. Not necessarily as mechanical energy, but it could turn into, like as it goes down the ramp, are we going to hear sounds? Are we going to, like all that kind of stuff, right? Energy is supposed to be conserved, okay? But obviously that's probably not going to look like that, because we're not going to be able to measure how much sound energy is produced. We'll be able to calculate it, but we won't be able to measure it. Okay? So the if part needs to talk about that law of conservation of energy, okay, theoretical relationship of energy at the top and energy at the bottom. The and part just describes the experiment. Okay, a cart is being run down a ramp. We're going to measure the height of the ramp. We're going to measure the speed of the cart at the bottom. Okay, those are the only 2 measurements we're making. In the then part, I just want your predicted results, okay? What do you think is going to happen and why? Okay, so we've said what is theoretically possible, okay? But I want your predicted results and a why as the then part of your hypothesis. This is a real world experiment. What is actually going to happen and why? This is probably the truest hypothesis you've written okay, in physics thus far, because you're actually having to predict what you think is going to happen. All right, so you've got a chart, okay, in your Google Doc there that looks like this, right? You're doing 3 trials, and what you need to measure is the height of the ramp. It should be around 15 centimeters, okay? It doesn't need to be much higher than that. I also wouldn't make it much lower than that, okay? 15 is kind of the sweet spot. 20 would be on the high end. 25, and it's getting to be so high that you don't collect enough data before it reaches the bottom of the ramp, okay? On that note, I would set the data collection rate to 20 hertz, okay? If it isn't already there, okay, because it's usually, I think, 10 by default, okay? It's in the bottom left corner of the display in SparkView when you have that, when you're setting it up, okay? Set it to 20 hertz so that it takes 20 measurements per second, okay, while the cart is rolling down the ramp. All right, so the only 2 things you need to record: height of the ramp, which is going to be the same number, all right? You're just going to write the same number, 1, 2, 3, and the same number for the average, because you're not manipulating the ramp at all. It's staying the same each and every time, okay? And then you're going to put down the maximum speed recorded by the SparkView app for each trial, right? We're not building a graph, nothing. All we have to do is look through that trial and grab the biggest velocity or speed number that it spits out. Okay? Everybody with me on that? All right. Now, when this thing rolls down the ramp, okay, please don't let it go off the bottom of the ramp. Okay? I mean, the ramp is still going to be on the ground, but it's a pretty jarring blow to those little plastic cart bodies each time it falls off, and the wheels have little like spring-loaded shock absorbers on them. So if you could have somebody just sitting at the bottom of the ramp to stop the cart at the bottom. Okay? The other reason for doing that is when it does go off the ramp, it falls just ever so slightly, and that gives a bit of an artificial jump in speed that we don't really want. We only want the data that's on the ramp, not that last little fall off the ramp, okay? So just have somebody at the bottom of the ramp that can just have the cart in their hands, okay? And then we'll get good data. And like I say, you don't need to build a graph or anything. You just export that data, look through the velocity column, pick the biggest number, and you're done, okay? That's the number that goes in here, okay? So realistically, there should be a pretty good chance of getting this whole lab report done in class today, because you don't have to build a graph, you don't have to analyze the graph or anything like that. Okay, for your analysis, okay, question number 1 is calculate the potential energy of the cart at the top of the ramp. Show your work. Okay, so I just want you to show me how you calculated the potential energy at the top of the ramp. Okay, then I want you to calculate the kinetic energy at the bottom of the ramp using the largest speed value from your SparkView data. Show your work. Okay, I just want to see that calculation. And that's just using the averages. So that's one calculation. Don't do it for every trial. It's using the averages. Question number 3, does the potential energy of the system equal the system's kinetic energy? Why or why not? Suggest reasons for your results. Okay, so does it equal, yes or no? Okay, why or why not? Okay, and suggest reasons why or why not. All right, question number 4, since friction does all the work in stopping the cart and the cart's mass is known, what is the coefficient of friction between the cart's wheels and bearings? Show your work. Okay, so this is going to involve 2 separate calculations for you. Okay, and those calculations will involve this, okay, and this. I'm not going to tell you any more than that. You can figure out how to use those 2 things, but those are the 2 things you're going to need to use in order to calculate the coefficient of friction for the cart as it rolls down the ramp. Okay, remember, we're losing this energy. Our prediction is that it's likely due to friction. Okay. All right, question number 5. What can this lab tell us about the efficiency of mechanical energy conversions? So for question number 5, I want you to do an efficiency calculation. Okay, so for question number 5, what I'm looking for is this. Okay, efficiency will equal our kinetic energy divided by our potential energy. That's essentially our final divided by our initial, right? It's not going to be, if it ends up being a number greater than 1, you got to bottle that, because holy smoke, you just found a way to create energy. and your efficiency is greater than 100%, and you're magic, godlike. Okay, so obviously if that's the case, you did something wrong. Okay, so you should get a decimal here. Okay, that's your efficiency percentage. Okay, have a look at that and then think about it. Okay, what does that tell us about a very simple energy conversion? Okay, was it pretty efficient, not efficient? What does that mean? Okay, so a little blurb there. Okay, and then for number 6, what would be some ways to increase the efficiency of this conversion? So just talk about a couple of ways that you could maybe make that conversion a little bit more efficient, okay, so that more of the potential turned into kinetic at the bottom of the ramp. Okay, then you got your conclusion, okay, copy paste your hypothesis, talk about your analysis and why it accepts or supports or refutes, and then 2 sources of error and ways to fix them. All right, questions on that? All right, ramps and carts are over on the side there. The plastic ramps are on the desk. The wooden ramps are on the cart. Carts are on the top shelf of the big red cart there. Okay, so this last thing that I want to point out to you that's going to be really, really important for one of your calculations has to do with number 4, okay, where you're calculating the coefficient of friction between the cart and the ramp. I want you to remember that when you're using this formula, okay, you're needing normal force. But you're on an incline. Okay? On a flat surface, normal force and what force are equal? Right. You're not on a level surface. So keep in mind that you are in fact on an inclined plane, okay, where you have gravity. And now, this side of the triangle that we've never basically ever used before, that now you'll need, okay? And that's fine, okay? You can get it, because you can calculate this angle. You know the length of the ramp, and you know the height of the ramp, so you can get that angle, okay? You know the mass of your cart, right? So you can calculate that normal force, but you need that normal force, okay? It's not equal to gravity in this situation because it's on an incline. Ask the question.
So like, I don't want to draw that on the computer.
Oh, you don't need to draw that. No, I mean like when you're doing your, if you want, just draw it on a piece of paper and then snap a picture of it, insert the picture.
Yeah.
Okay?
We don't have to do that, we can just figure out what
Yeah, I mean I'd still like to see you I'd like to see your calculations for that.
Yeah.
Yeah. Okay, everybody with me on that? All right.